The gas planets. What are these monsters of our planetary system? Some of them up to 12 times the size of Earth. They differ not only by their composition, but by their size. Gas planets or gas giants are indeed much bigger than their terrestrial neighbors. Why are they so big? What are they made of? Where are we in our knowledge of these celestial? What missions, past, present or future, will discover their secrets? Before we go ferreting in the poisonous fogs of Jupiter, Saturn and their satellites, let us go back to the formation of the system into which they were born, in order to understand their mystery and their influence on other astral bodies in the Milky Way.
We have been given the scientific knowledge, the technical ability, and the materials to pursue the exploration of the universe.
After the collapse of a nebula about 4.5 billion years ago, our solar system began its adventure with the creation of its star, the Sun. The temperature at the heart of these fusions reached 15 million degrees. Nuclear reactions occurred one after another. 50 million years later, the Sun is still only a protostar, a great mass formed by the contraction of gases from a molecular cloud composed mainly of hydrogen and helium. It is a gigantic cloud of dust and other matter. 10 million years on, 4 planets have formed. They are known to us as the gas giants: Jupiter, Saturn, Uranus, and Neptune. It has been observed that in general, in the rest of the universe, gas giants like Jupiter tend to move closer to their star, sometimes going so far as to throw themselves into it and disappear. Jupiter and Saturn are therefore the exceptions. And then we come to a very special phase in the solar system, around quite a number of stars other than the Sun. Other giant planets like Jupiter have been observed, but only at a few kilometers from their nearest star. They are burning. These are known as hot or superhot Jupiters, but this is not what happened in our own solar system. We still have a cold Jupiter, at least at a distance, and this is exceptional. We find only very few if we look around. So what could have happened? Many scenarios are possible. The most popular is the idea that in the solar system we were fortunate in that while Jupiter was forming a little further on, and probably because there was a great deal of matter and ice, another planet was forming, Saturn. And the two together show a particular behavior. Jupiter wasn't alone. Jupiter inevitably started getting nearer to the Sun. It migrated, so it moved towards the Sun very slowly in a spiral path. And Saturn followed. And we can show by sophisticated calculations that each time that they are next to each other, they apply a sort of gravity. And we realize that sometimes, for example, when one of them makes an orbit, the other makes two. It creates a sort of resonance. And at that moment, it seems that Saturn prevented Jupiter from getting closer to the Sun by catching up with it. And the two together came back towards the outside, to the positions they occupy today. So all the same, in this scenario, Jupiter came close to the Earth's orbit, and now it's 5 times further from the Sun than the Earth. It came close to the position where Mars is now. That's one explanation as to why Mars is much smaller than the Earth, of much smaller mass. Perhaps a large part of the matter which later formed Mars was swallowed up by Jupiter when it passed that way. But then it went off in the other direction. In our jargon, we call this the grand tack, this round trip of Jupiter and Saturn. Thus, the solar system is composed in the following manner. The Sun, around which the other celestial bodies gravitate. 4 interior terrestrial planets: Mercury, Venus, Earth, and Mars. The belt of asteroids, which is composed of small lumps of rock. 4 giant planets at the outside, of which 2 are the gas giants, Jupiter and Saturn. 2 giant icy planets, Uranus and Neptune. And the Kuiper belt, composed of icy fragments. A gas planet or gas giant, also known as a Jovian planet or giant Jovian planet in reference to Jupiter, is one composed mainly of hydrogen and helium. The solar system has 2 of this category: Jupiter and Saturn. At the end of the 1940s, a study of the composition of Uranus and Neptune showed how they were different from Jupiter and Saturn. During their formation, Uranus and Neptune incorporated matter in the form of ice or of gas trapped in the ice of water. Thus, these planets are composed of volatile elements heavier than hydrogen and helium, such as water, methane, and ammonia. So they became known as ice giants. In reality, there are still many gaps in our knowledge of the structure of these enormous planets. It is typified by the presence of several bands of cloud composed mainly of water and ammonia. Their internal structure would seem to be formed of an external layer of gaseous molecular hydrogen, which becomes liquid in depth and covers a layer of liquid metallic hydrogen, enclosing, no doubt, a rocky and icy core. There's only one Jupiter in the solar system, and it's a cold Jupiter. On the other hand, we've discovered around us other giant planets like Jupiter, but much closer to their star, so we call them hot Jupiters. They're very well known, these planets, because they were the first to be discovered. The very first discovery was around the star Pegasus 51, a Jupiter which was so close to its star that it made its orbit in 4 days, so a 4-day year. And what's more, with its covering of cloud, which almost certainly reached more than 1,000 degrees, very hot Jupiters. So afterwards, there's a whole history, a group of Jupiters between those that are very close, those a little further away, and those close to Earth's position. So we could imagine perhaps satellites which could be at a temperature allowing liquid water, with oceans perhaps even going as far as cold Jupiters. There's even an ultra-hot category of Jupiters. These are planets which have just formed, so not only are they heated by their star, which is young and powerful, but also, since they're newly formed, all the energy which comes from these different comets and different things which constituted these enormous planets makes all this energy which comes falling upon them each time. It gets hotter and hotter and hotter, which means that an ultra-burning Jupiter gives us an ultra-hot Jupiter. It so happens that Jupiter is approximately a little over 300 times the mass of the Earth, Saturn a little over 100 times the mass of the Earth. So if we're looking at a planet that is 100 times more massive than Earth, we call it a Saturn. One might think that it's because it has a ring round it. When we think of Saturn, we think of its beautiful ring, but that's not the reason. It's only a question of size. Then there are Neptunes, which are about 15 to 20 times the mass of Earth. Neptune has 17 times the mass of Earth, and there are even mini Neptunes with a mass of around 10 times the mass of Earth, even 5 times the mass of Earth. You never know. When we find a planet 5 times the mass of Earth, whether it's a planet surrounded by hydrogen like Neptune, so a mini Neptune, or it's a rocky planet with a thin atmosphere, then it's a super Earth. Jupiter is the biggest planet in our solar system. It bears the name of the king of the Roman gods, Zeus in Greek, and is therefore destined to rule over the other planets. At the beginning of the 17th century, in 1610, and thanks to Galileo's invention of the astronomical telescope, Jupiter and its 4 satellites were discovered. To observe and establish that the Earth was not the only body possessing satellites was a revolution at that time, because the Earth was still considered the center of the universe. The radius of Jupiter is roughly 12 times that of the Earth, and its mass is nearly 320 times more. We have no certainty about the actual composition of Jupiter. For example, we don't know whether it possesses a core. Numerous theories abound. In standard terms, its internal composition as a gas planet would be mainly made of hydrogen and helium. Jupiter's surface is composed of several quite distinct layers. Thus, these movements of gas are tinted by the chemical reaction which takes place, and by the rays of the sun. These phenomena are constantly changing. In May 2010, one of the widest brown layers disappeared almost completely. Then reappeared a while afterwards, as if by magic. These constant movements create huge storms, vortices, and giant hurricanes. But there is one which dominates all the others. The Great Red Spot is a gigantic anticyclone in Jupiter's atmosphere. Its diameter is about 15,700 kilometers and is therefore bigger than the Earth. The storms there can blow at up to 700 kilometers an hour. Its age is not known, but we do have evidence of sightings of it since 1665, more than 350 years ago. Cassini was the first to observe it and to determine the rotation period of Jupiter. It was only given the name of the Great Red Spot in about 1878. It was Voyager 1 in February 1979 that revealed the first images of the Great Red Spot. After that, the missions of NASA, Cassini-Huygens, and more recently Juno provided more detailed images with a resolution of 60 kilometers. Studies indicate that the stability of the Great Red Spot could result from the absence of solid surfaces and a natural tendency to absorb the surrounding turbulence. Caught between two opposing flows, it may draw energy from both. Thus, this could be a permanent characteristic of the planet. But during the time scientists have been observing it, the Great Red Spot has got smaller. It measured more than 40,000 kilometers, enough to swallow 3 times the Earth. Today, it has diminished by nearly 60%. Its shape is becoming rounder, which leads some to think that it could end up by becoming unstable and finally disappear within about 20 years. But this is just theory. As so often with Jupiter, there is no consensus on the question. Owing to its very great speed of rotation, Jupiter is subjected to enormous centrifugal forces. It is therefore squeezed by about 6% round the equator. To send a mission to study Jupiter is quite complicated. Firstly, Jupiter is not next door. It's much further away than Mars. It's distant by 5 times the distance between Earth and the Sun, so it would typically take about 4 years to reach it. What's more, once one arrives in orbit around Jupiter, one has a certain number of problems. First, as it's far away from the Sun, there's very little solar energy. So either one takes along a source of nuclear energy, as was done, for example, for the Galileo mission in the 90s, or you carry enormous solar panels. Since it receives about 30 times less solar energy than Earth, you'd need solar panels 30 times larger. Apart from that, Jupiter, this enormous planet, has a very strong magnetic field, which means that the whole surrounding area is more or less radioactive. What I mean by that is that there's an enormous number of particles of ions that move very rapidly and impact anything electronic, and which, if you don't protect it, would cause any probe to break down. So the probes that are sent around Jupiter are armored, and that means more weight. You have to armor the probes. They're real tanks. So shield the probes that are sent around Jupiter. And finally, the ultimate difficulty if you want to land on Jupiter is not really possible because it's a gas planet. In any case, if you want to send a probe into Jupiter's clouds, that's already been done by the Galileo probe in the 90s. And then is the problem of the extremely strong gravity, much stronger than that of Earth, which means that if you shoot down onto Jupiter, you arrive at enormous speed and you need a very thick protecting shield, which makes the thing very difficult. But the Americans managed it once, and it was a great achievement. The Cassini-Huygens probe, heading for Saturn in December 2000, took high-resolution images of Jupiter and studied its magnetosphere. It showed itself to be much higher than predicted. Probe Juno launched in August 2011 for a 5-year journey. In October 2013, it made use of the gravitational pull of the Earth. It finally reached Jupiter on the 5th of July 2016. The aims of the mission were to study the origin and the evolution of Jupiter in order to better understand the formation of the solar system, given that the planet, unlike the Earth, has kept its initial composition. Our knowledge of Jupiter took a leap forward with the Juno mission. But quite apart from the scientific advances, Juno gave us outstanding pictures of the Jovian system. Mission Juno was the first to be dedicated entirely to the planet Jupiter itself, not counting surrounding satellites and moons. That was the choice. A polar orbit was chosen. So it circled around the planet. And so, for the first time, we were able to discover Jupiter's poles, map the magnetic field, and also to study the nature of this incredibly complicated atmospheric circulation that one can only guess at from the photos of Jupiter. One can see its whirlwinds, the geysers spurting in every direction, and one has to ask oneself many questions concerning these geysers. Could they be very superficial, something like those on Earth, that's to say just a few kilometers deep? There are clouds of ammonia and water clouds. It's quite exotic, with all those colors that we don't really understand. On the other hand, can it be that the jets we see there, which cause the clouds to move like that, are really deep and go almost to the center of the planet? Juno was conceived in order to conduct this ultra-technical study, to examine the gravity field using a sort of microwave probe. To describe it in simple terms, to look deep into the center of the atmosphere. And in the end, Juno's aim was not to take the wonderful photographs which we find so fascinating. To the extent that the Juno cam, the camera for the probe, was not even considered to be a scientific instrument. It had no scientific team associated with it. The images arrive on Earth and are made available to the public at large, who can show them and make whatever scientific analyses they wish. You have just these images, and yet the images are the most spectacular part. Frankly, Jupiter is one of the most beautiful objects one can imagine, one of the most beautiful in the solar system at least. And in particular, we've discovered not only what's happening at the equator, which had already been studied by the previous missions, Voyager, Galileo, etc., but also the polar regions. And there amazing discoveries were made. At the South Pole and the North Pole, one sees sort of vortices which intertwine with a central vortex and an atmospheric dynamic on an enormous scale of thousands and thousands of kilometers, extremely complex, like an incredible natural laboratory, which we don't understand very well, and which gives us food for thought. As well as all this activity that Juno maps, extraordinary, magnificent aurora and lightning strikes. Incredible storms with lightning that last 10 times longer than on Earth, etc., etc. So Jupiter will no doubt keep its secrets for a long time to come. On the other hand, the observation of its moons could turn out to be more accessible. Io, Europa, Ganymede, and Callisto are Galilean moons. And finally, space exploration has shown us that those 4 little points of light that we saw orbiting Jupiter, each one of them is an extraordinary world. Io, on which there are constant volcanic eruptions. Europa, with its ocean under a thin crust of ice, are just waiting to be explored. Ganymede, with its magnetic field, Callisto, truly enigmatic. We've made discoveries, but I must say that what comes out of all that is that there are still a great many questions. So much to explore, because each of these moons is a world in itself. Fortunately, there are space missions planned to explore in more detail. The European Union is going to launch the JUICE mission next year to study the moon Europa, to some extent, but mainly Ganymede, an incredible world. We will know much more about it when we have those observations, and it will be followed shortly afterwards by a huge American mission, Europa Clipper, whose aim is to discover, by going into orbit around Jupiter, what is happening on Europa, and to determine once and for all if there really is an ocean. We're almost sure there is, but also to look at where the water might flow out. If we can get an idea of what is happening inside, and if we find frozen dead prawns, we will hold very important information. I don't think it's likely, but that's the essence of the mission. Saturn is the 2nd biggest planet in the solar system, and the 6th away from the Sun. Its mass is 95 times that of the Earth, and 900 times its volume. It completes one orbit in 29 years and 167 days. Saturn is the least dense of the planets, being 0.17 times lower than that of water, so it could float in a vast swimming pool. Like Jupiter, Saturn turns very fast, as its rotation time lasts 10 hours and 39 minutes. This causes enormous centrifugal forces that squash the planet. So we can observe a difference of 10% in width between the poles and the equator. Saturn is composed of approximately 3/4 oxygen and 1/4 helium, with traces of water, methane, and ammonia. similar to the primordial nebula when the solar system was formed. Saturn gives out 1.8 times more energy than it receives, thanks to its great internal source of energy. The temperature at its center reaches 12,000 degrees Celsius. Like Jupiter, Saturn and its array of satellites forms a miniature planetary system. Saturn is probably made up of a rocky nucleus wrapped in metallic hydrogen. Then its layer of atmosphere, formed mainly of hydrogen and helium. Being further from the Sun than Jupiter, Saturn's atmosphere is colder. Its storms are less violent. But that does not stop it having a number of exceptional phenomena. Indeed, in 2010, a massive storm 300,000 kilometers across was photographed by the Cassini probe. These abnormal gas giants create incredible atmospheric phenomena. That particular storm ended up entirely covering the planet's northern ice cap. Just like Jupiter with its great red spot, Saturn too has its jewels. In its northern hemisphere, Saturn has a most unusual shape. A hexagonal formation with almost perfect sides. How can a group of clouds create such geometric perfection? It was probably a storm of more than 32,000 kilometers in diameter, whipped by winds of up to 500 kilometers an hour. It was discovered by one of the probes of the Voyager mission at the beginning of the 1980s, and was investigated once again by the Cassini-Huygens mission in 2006. The hexagon on Saturn is extraordinary because it's geometrically perfect. We have to remember that one of its sides is much bigger than the Earth. So there we have a sort of natural laboratory that's much bigger than the Earth and creates fluid mechanics, like in a laboratory, and we're trying to understand it. In a lab, we could understand it. It was a maybe. When you produce a jet stream like that, wind rotating around a pole, you can, in certain conditions, reproduce that hexagonal shape linked to what are called Rossby waves, enormous vortices which form just like that, which organize the jet stream. But it's one thing to make it in a laboratory this big, and something else to see it on a planet with a diameter of several tens of thousands of kilometers. In 1610, using his astronomical telescope, Galileo observed Saturn. He noticed something strange on each side of the planet. Nearly 50 years later, in 1656, Christian Huygens solved the mystery. In fact, they were rings. Over the 28 years it takes Saturn to orbit the Sun, these rings are seen alternately from their edge and then more opened up, which explains the changes in their appearance seen through the imperfect telescopes of the time. The rings are composed mainly of frozen water. One of the fascinating aspects of these rings is their size and their layout. In fact, they have a phenomenal diameter of nearly 250,000 kilometers, while they're only about 10 meters thick. Their observation by the probes and satellites from Voyager in November 1980 revealed a magnificent system of an incalculable number of billions of rocks orbiting around Saturn and forming thousands of stunning structures. Divided into 7 different categories, Saturn has 3 main rings, named A, B, and C, in their order of discovery. At first, rings A and B were part of the same group, until Cassini discovered a division that now bears its name. It demonstrates that the rings were not homogeneous and were probably formed by a plethora of small satellites. Ring A has within itself another division, the Encke division, caused by the orbit of the moon of Pan. Another surprising phenomenon is that ring F is relatively narrow. It's separated from ring A by 2 moons, Prometheus and Pandora, who maintain the elements around this orbit, seen here by the Cassini probe. Saturn was visited 3 times in the 20th century by Pioneer 11, Voyager 1, and Voyager 2. These vessels, designed to explore the solar system, only flew past. The Cassini probe orbited them for 13 years between 2004 and September 2017. It turned our knowledge of Saturn on its head. On its last mission, Cassini flew between Saturn and its first ring. In 2017, Cassini was more than 1.5 billion kilometers away from Pasadena. The probe had been in orbit around Saturn for nearly 10 years, and more specifically, around one of its moons, Titan. Although it hadn't been destined for such a mission, the probe was to explore this ostensibly empty region between Saturn and its first ring. The speed of the probe, 12,000 kilometers an hour, meant that any collision with the slightest particle of the ring would be enough to destroy it. Everything unfolded as planned. The probe would study the composition of Saturn for 5 months and get results that were unthinkable up to then, namely, to find out the compositions of the heart of Saturn. Another thorny question might find an answer here. How old are Saturn's rings? A few 100 million years or 4 billion? The probe managed without problems to fly between the ring and the planet. For 5 months, it repeated the flight once a week. But on the 15th of September 2017, Cassini, for the last time, plunged into Saturn's clouds. Cassini-Huygens was a really extraordinary milestone in exploration. Obviously, Cassini was in orbit around Saturn, and you might think that was all it did, just mindlessly mapping Saturn. Not at all, because obviously Saturn's system is a very rich system with a diversity of extremely interesting moons, the rings that had to be explored, and Saturn itself with its very surprising atmosphere. That's why the Cassini probe was put into orbit around Saturn. And it launched the Huygens probe that landed on Titan in 2005. And then it undertook quite a fascinating sort of exploration, which has to be seen when we visualize it, because it went to have a look at Titan, for example. And using Titan's gravity, it bounced up again and went off to visit another moon and bounced up again. Which means that if you see Cassini's orbits, it's a sort of stroll around Saturn, sometimes near, sometimes further away. It comes close, has a look at the rings, bounces up, and it's off again to slip between Saturn and the rings, very close, and then flies off into Saturn's atmosphere. So it isn't really an observation satellite that is systematically mapping the world of Saturn. It is really a sort of exploring, adventuring emissary, exploring a sort of collection of worlds in a whole system, that is Saturn's system. Man discovered Saturn's satellite system in 1655. Huygens was the first one to see Titan. Since then, 82 satellites have been officially registered. The biggest of them, Titan, was also called Saturn VI. It has a diameter of nearly 5,000 kilometers. The surface temperature is extremely cold, about -100 degrees Celsius. The atmosphere of Titan, the only moon in our solar system that has one, and which, what's more, is very dense, is composed of hydrocarbons, which make it almost completely opaque. So it isn't possible to inspect it visually. Only sending a probe into it could solve the mystery of the surface of Titan. Is it liquid or solid? In December 2004, Cassini launched the landing module Huygens, whose mission was to land on Titan and study it. Released from the Cassini probe, it took 3 weeks to reach Titan. A complex 3-parachute system enabled the descent. After the last parachute opened about 100 kilometers from the surface, the descent lasted about 2.5 hours. The landing was a success. It is still today the most distant landing carried out by man. The 127 overflights of the Cassini probe and, of course, the Huygens probe's penetration of the atmosphere and its landing have shown the existence of complex organic chemistry in the atmosphere. The many clouds are formed of methane vapor. At Titan's poles, there are lakes and seas similar to those on Earth, but they're made of liquid methane. If we go deep inside the crust, Titan is made of frozen water. The temperature rises, and it's thought that at a certain depth you come to an ocean of liquid water. The same thing exists on Ganymede, on Europa, etc. What's so exciting on Titan is that this ocean is perhaps connected to the surface of that moon. And it's thought that at the surface there's a very complex organic chemistry, because highly complex organic molecules, polymers, soot from a sort of plastic, form and fall onto the surface, end up in the lakes, and may filter into the inside of the planet. And therefore the very deep liquid water oceans of Titan are seeded by the organic molecules which are conducive to life. And this gives rise to all sorts of speculation, since more so than on other worlds there is really ice, ice and more ice. Here there's ice with many, many organic molecules that could have contributed to starting a form of exotic chemistry, even life itself. Faced with this mystery, which is still to be elucidated, NASA has officially validated the development of the first airborne exploratory mission, Dragonfly. To be launched in 2026, this octocopter should be able, around 2034, to navigate in Titan's atmosphere to analyze the composition of its surface. Full of cameras and other instruments, it will be able to analyze the soil in its onboard laboratories. After it drills into the ground, it will take samples and put them through tests to fine-tune the results and determine what are the key elements present in the ground. Titan presents a veritable laboratory for the production of organic molecules. Like the Earth, it is the only other known world on whose surface one finds stretches of liquid. Titan has 10 times more areas of liquid than all our oceans put together. For this reason, NASA, with its Research Institute for the Study of Exceptional Environments, has conceived the first space submarine, the Sub. "5.9 meters long, 1.01 meters wide, and 2 meters high, the Sub should complete a period of 90 days in one of Titan's seas." The submarine is designed to discover if a living organism could have developed in the satellite's liquid methane. In February 2005, Cassini witnessed an eruption of a strange plume of mist at the surface of the moon Enceladus. This discovery set the scientific world on fire. Enceladus is a small moon in Saturn's E ring. It reflects very brightly the light that falls on it, which indicates a surface covered with water ice. As with many similar moons, the movements of Enceladus indicate the presence, under 40 kilometers of ice, of a global ocean of liquid water surrounding a core of silicates, probably porous, in which the water can penetrate, warm up, and rise again into the hidden ocean in the form of hydrothermal springs. It was suspected that, as with Europa, it was cryovolcanism. This theory was confirmed in 2005 when Cassini filmed surface eruptions in the moon's southern hemisphere. These eruptions rose several hundred kilometers above the surface. The probe even had the chance, during one of its passes, to go through one of these geysers. It was able to detect organic molecules. And with liquid water, organic molecules, and a source of hydrothermal energy at the heart of the moon, we have the ingredients to support life. Is life possible? As yet, nobody knows. But together, Titan, Europa, and Enceladus present the most promising trio of the solar system. Let us continue our journey a little further even from the Sun. Our first meeting beyond Saturn is Uranus. And then Neptune. The ice giants Uranus and Neptune, in their cloud blankets, are in fact mainly composed of liquid elements. Although the two giants are of similar size, Uranus has less mass than Neptune. They are also different by the inclination of their rotational axes. The axis of Uranus is unique in the solar system in being laid down in the plane of its orbit. The planet seems to roll around the Sun. Although less complex than Saturn, Uranus also has its system of rings. We see here 13 in this photograph by the Hubble telescope. Another explorer was privileged to witness these distant encounters: the Voyager probe. After a journey of more than 2 billion kilometers, Voyager sent back photos of icy, unexplored worlds. Uranus would seem to have a very deep ocean, which would explain the planet's magnetic field, and a rocky core the size of Earth. The magnetic field of Uranus is widely displaced from the center of the planet. When Voyager trained its cameras on the rings of Uranus, it discovered a new light. Voyager continues its travels to the limits of the solar system, towards a new encounter. The eighth planet of the solar system, Neptune, is the farthest away from the Sun. It revolves around the Sun at a distance of about 4.5 billion kilometers. Its period of orbit is 164.79 years. It's the third planet in terms of mass of the solar system and the fourth largest. It is also the densest of the planets. Neptune is the first celestial object and the only one of the 8 planets of the solar system to have been discovered by mathematical calculations rather than empirical observation. Indeed, the French astronomer Alexis Bouvard noticed unexplained gravitational irregularities in the orbit of Uranus. The existence of another planet invisible to the naked eye was therefore postulated. The British astronomer John Couch Adams in 1843 and the Frenchman Urbain Le Verrier in 1846 independently worked on the calculation of the position of this potential planet. It was finally observed for the first time on the 23rd of September 1846 by the Prussian astronomer Johann Gottfried Galle at 1 degree from the predicted position. Its largest moon, Triton, was discovered 17 days later by William Lassen. This is the only stellar object to orbit in the opposite direction from the rotation of its planet. Covered in iced nitrogen, it's one of the coldest objects in the solar system, with a temperature of minus 135 degrees Celsius on its surface. The atmosphere of Neptune shows active and visible meteorological conditions. The strongest winds in the solar system have been measured on Neptune, reaching speeds of 2,100 kilometers an hour. It has been realized that around other stars, the most usual planets that one can see are of the type Uranus and Neptune, cooler or hotter, etc. But typically, it's the usual planets that we see 10 times, 15 times, 20 times the mass of Earth, the equivalent to Uranus and Neptune. So to understand these exoplanets, we probably need to better understand Uranus and Neptune. In this context, everyone wants to go and explore, come back, study in detail the ice giants, and although it's not yet official, everything points to the idea that NASA, hopefully accompanied by European scientists of the European Space Agency, will prepare a mission to Uranus and Neptune. It's the subject of a current wide-ranging review of NASA projects called the Decadal Survey. NASA reviews its program every 10 years, and everything points to the priority number 1 being the project of returning to Uranus and Neptune to study and understand them. So our journey through the gas giants ends here. But it is doubtless only the end of the beginning.